How can we make equivariant neural networks and machine learning force fields efficient? We introduced the Tensor Decomposition Network, TDN, which accelerates force field computations while preserving equivariance and accuracy. So what is Machine Learning Interatomic Potentials? A machine learning interatomic potential is a data-driven interatomic potential trained on quantum mechanical data to predict atomic energies and forces, enabling molecular simulations with near ab initio accuracy at far lower cost. Machine learning force fields must respect symmetry. Energy is invariant to rotation transformation, and forces are equivariant to rotation transformation. Vanilla MLPs on point clouds don't enforce this. So, how can we achieve this? To keep our network faithful to 3D rotations, we use the Klebsch-Gordon tensor product, the standard way to combine two rotation feature blocks while staying equivariant. The challenge is that as you raise the maximum angular degree, the number of combinations explodes. The runtime grows roughly with the sixth power of that degree, which becomes a major bottleneck. Let us do acceleration. First, we simplify the representation of the Klebsch-Gordon tensor product. We rewrite it as a single core tensor operation. Any pairwise interaction between two rotation feature blocks can be captured by one core tensor applied to their combined features. As shown on the bottom, fusing the two blocks becomes one tensor multiply instead of many branching paths. The core is extremely sparse and repeats values, so we exploit that with tensor decomposition. Now we perform tensor decomposition. We compress the CG core with tensor decomposition, as shown in the figure. Instead of one huge three-way table of numbers, we express it as a sum of our simple pieces. Practically, that turns fusion into 4 steps. Project the first features, project the second features, multiply them channel by channel, then do a final linear mix. It's all matrix multiplies plus a lightweight per channel product, fast and GPU friendly. For better demonstration, let's step into the tensor decomposition pipeline. We start with 2 input NeurIPS feature blocks, as shown in the figure. We form their outer product, pairing every component of one with every component of the other, then mapped by the core tensor M. We then obtain the result NeurIPS Z. Next, we factor the core M with tensor decomposition, a sum of our rank 1 components built from 3 factor matrices A, B, and C. Each rank 1 term acts as a tiny map. It takes the input NeurIPS and produces one output component, as shown in the figure. This is a whole pipeline of using tensor decomposition. The total time complexity is the rank multiplying L squared. We pick the rank automatically with a rank scheduler that ties it to the maximum angular degree. After comparing several schedulers, we use rank is almost equal to 7 times degree squared, which keeps accuracy high and brings total runtime down to roughly the 4th power of angular degree. Plus, to shrink parameters in memory, we use path weight sharing. Instead of separate weight for every Klebsch-Gordon path, we use one shared weight block. This changes scaling from cubic in degree to constant while keeping equivariance. We fuse tensor decomposition and path weight sharing into a graph transformer, giving us tensor decomposition networks, TDNs. This replaces costly Klebsch-Gordon coupling with low-rank core and shared weights. In practice, TDN runs faster than CG-based layers and delivers higher throughput with fewer parameters than equiformer. We evaluate TDN on the OC20IS2 RE benchmark. By keeping a tensor product interaction at its core in factorized form, TDN preserves expressivity while being far more efficient. We also evaluate on PubChem QCR. TDN preserves expressivity while staying efficient. Finally, we evaluate TDN over OC22IS2 RE benchmark. We achieve competitive results over other baselines. Thank you for your listening. To explore more, check out our QR code below.